This video complements our vision paper towards immersive software archaeology, regaining legacy systems design knowledge via interactive exploration and virtual reality. State-of-the-art software systems that are being actively developed today will become the legacy systems of tomorrow. Their original developers will eventually move on to other projects, and their technology will become outdated. Ultimately, legacy systems may not be able to meet new requirements, such as to accommodate for a new environment, increased load, or changed legislation. Nevertheless, many legacy systems are important assets, so that their companies have a strong interest in keeping them up and running. A company might then want to re-engineer their legacy system, where a major aspect is to understand it. Software archaeology aims at understanding the structure and behavior of a system, while examining its quality in search of potential for improvement. However, software archaeology faces an inherent challenge. Usually, legacy software systems are large-scale solutions. Manually browsing through thousands of lines of code is infeasible, while consulting the original developers is often also not possible. Thus, computer-aided software comprehension tools play a key role in software archaeology. These analyze the subject system and present their results in textual or visual form. However, even when equipped with such tools, exploring an unfamiliar codebase still requires significant effort, motivation, and diligence, which at present makes recovering design knowledge a challenging and tedious procedure. Our vision of immersive software archaeology provides remedy for that. We will use virtual reality to immerse software archaeologists into an engaging 3D visualization of an object-oriented legacy system. Thereby, we aim at lowering the entry barrier for understanding complex systems and strengthening users' mental model for their design, behavior, and quality. To make best use of humans' visual cognitive abilities, we will use a real-world metaphor to generate a virtual three-dimensional representation of a subject system. In contrast to many existing software visualizations, we will not rigidly visualize all fine-grained implementation artifacts at once. Instead, we will provide additional layers of abstraction by automatically detecting components in terms of hierarchically nested, cohesive units of functionality. On the highest level, we will visualize these as planets. Lower-level components will be visualized as continents, and on the lowest level as cities. Users can travel among these and thus explore the system from its inside. This is how that concept looks like in our current, very early stage prototype. Our entire visualization will be tailored towards easy usage in virtual reality. For instance, we will provide users with a mechanism to quickly navigate along the different levels of structural abstraction, such as from solar system level to city level. In a city, buildings will represent classes. The individual floors will represent class methods. To achieve a high level of immersion, our entire VR experience will be highly interactable. Detailed information will be available on demand, displayed on diegetic interfaces attached to objects in the virtual world space. At the same time, we will convey a subliminal feeling of a subject system's quality by texturing elements according to automatically analyzed quality properties. For instance, one part of this building has a rather brittle-looking facade. Attracted by that phenomenon, users can trigger a detail view. The visualized method here seems to access a lot of data from one other class, which makes it fragile towards changes in that class. Other observable phenomena will be inhabitants of the solar system, who walk along routes such as the streets of a city. These inhabitants will represent the behavior of a system, as captured in pre-recorded runtime traces. It will thereby be possible to quickly identify heavily frequented routes within a system. We will provide means that allow to carefully examine and time travel debug a system's behavior by manipulating its execution speed. It will be possible to pause, play, speed up and down, as well as to jump back and forth in time, allowing to inspect both short-lived phenomena and lengthy procedures. Another important aspect will be a tight integration with an IDE. By that, we do not only mean that source code will be available in VR. We will additionally enable users to annotate points of interest by attaching sticky posts to elements of the VR world. These can contain drawings and sound recordings, which are then synchronized and made available within the IDE. Furthermore, users will be able to create guided tours through a system, reaching from one annotated point of interest to another. That can ease the introduction into a system for new collaborators. With our envisioned method, we aim to reshape the comprehension phase of legacy software system re-engineering, to cope with an increased number of legacy systems of the future. Instead of being labor-intensive, tedious work, we will immerse re-engineers in an engaging, playful exploration that builds a strong mental model of a system while still connecting to its implementation. We investigate that in our project Immersive Software Archaeology.